that's the only way this works. So I'm going to go back to redefine the beta V group, not that it's really necessary. It helps index things. So, question? Oh yeah, right. This line is so F is a p-adic field. Galois group gamma F, and so containing the inertia group, and the quotient is the Galois group of the residue field. So this contains the geometric Frobenius, which is invoked but not defined. So let me say this. So this is Q F. And then two-step filtration in the inertia group. Sometimes this is written yellow 1 to indicate the way Frobenius acts, but just leave that out. Where this is a wild ramification, this is pro P, and this is all prime. Now, if we have a map to GL and C, then the continuous, then the image of sigma is solvable. Fact, and sigma wild ramification is nilpotent. And this is still true if gamma F is replaced by the Weil group of F. Now, somehow, this kind of continuity is not enough to capture what's going on with p-adic or correlatic representations, but it's not so far off. So let's see. I defined the reciprocity map. I don't like this notation, but it's convenient. Which sends a uniformizer to modulo O star to Frobenius modulo. And this identifies this notation for G F is one-dimensional representation of the Weil group with A1F, which are irreducible representations of F star. That's local class field theory. And now the local Langlands correspondence for GLN replaces this one by N. So back up. Oh, maybe I should just say this. I'm going to refer to it again. So remark. This is remark for the board I just erased. If n time to p and sigma is irreducible, sigma representation is a complex representation. Then, well, the image sigma is a group of order prime to p, so that well, that's so that then actually then sigma pf is central. So that's simplifies things considerably. All right, but now let me get back to where I was. So now WDF, the magnetic. So a representation, so an n-dimensional representation, WDF is a pair, rho n, where rho, so over, so coefficients in whatever field, K, so V, K dimension n, and this is just, is a, well, it's a, it's going to be a representation with the image of PF of IF finite. So I want to be continuous for K over topology. And then N, the nilpotent endomorphism, such that for all G, F, G, that's rho N, rho of G, inverse, equals the norm of G times N, where the norm F to Q Z is just composite. Star, and then this is the absolute value. So that in particular, the uniformized averages, Q inverse, and this is consistent with what was defined yesterday. So now G and F is this set of equivalence classes such, and inside G 0 and F is the irreducible. So in particular, this N is 0. So, meanwhile, A and F is the set of irreducible, admissible representation over K, I guess. Again, these are topology. There's no role of well, you can think of K as C of G L and F, and inside A 0 and F, which is a supercustom. So, local Langlands correspondence. Is a family of bijections just one bijection, but a family of bijections sigma says N and F vary between A and F and G and F. Now, if you don't ask for anything more than that, so there's a normal, let me give you one normalization condition. The central character, C pi, the central character, pi corresponds to the determinant of sigma. one normalization already. Down. So, if no more conditions are opposed than that, then the existence of such a bijection or such a family of bijections was proved by Young. So this is proved in 2 stages. Historically, in reverse order. First, there's a reduction to a bijection between A0 and F and U0 and F. And this is due to a Bernstein Zelevinsky around 1979, I think. And then the proof, the second part, is the existence of such a bijection. So this is structural.
You need to add.
Sorry?
Both sets are countable.
Absolutely. I was going to say
as a conductor condition, maybe.
right. Absolutely. Absolutely.
Not empty.
Yeah. Yes. Exactly. So there, of course, one knows. Depends. If you twist by a general character, then they're not countable, are they? They're uncountable.
But you fix there. Oh.
It makes it even worse.
It makes it even worse, right? So I was getting to that. So yes, I was getting to that. So let me say. So this is structural in the sense that one can determine the general object of this kind in terms of the irreducible by putting some of them together as a direct sum and then putting. After it's been turned into a sensible question, after one has broken up both sides into finite sets. So one can do this by fixing the central character and then fixing the conductor. So, in fact, Ennia's theorem is this. This is that, let's, yeah, I have funny notation. So, okay, so let me write that one. Funny, never to be reused notation. So I'll call A, 0, N, F, brackets A to be the set of representation, so supercuscular representation with conductor A is pi equals A is an integer, and modulo twists by characters. And then G, 0, and F. A to be irreducible representations of WF with Arkin conductor A, sigma of A modulo twist by one-dimensional representations. And then Anyhow's theorem, so all A, there's a bijection A0 and F A. They have the same number of elements. These are finite sets, so that now makes sense. They can be counted in any sense. All right, so that was around 1986. Now, anyhow, also, was I think the first one to observe that even if you put in a few additional conditions like compatibility with twists, such bijections are not unique. But he did prove the following theorem. There is at most one, this is for fixed n fixed f normalized bijection. Well, actually it's not fixed f and maybe n vary. Bijection compatible with conditions 3, 4, 7, and 8 below. Below means here. This is so assuming. So this is to say that so for fixed, this is A0 and F, G0 and F, for F fixed and N fixed, assuming somehow known for M. And then the local Langlands correspondence. Which is proved by two global arguments. 1998. Well, there is a correspondence, a family of correspondences. From A and F to G and F, satisfying let's say max. So one, so pi with the sigma pi is a bijection. The bijection identifies A0 and F with G0 and F. Let pi be in A1F, which we identify with G1F theory. Then sigma pi determinant is equal to sigma pi. And so chi is one particular for n equals 1. This is just local classification theory. Also, about the other condition, C I equals the determinant sigma via this identification. So I said 3, 4, so here comes an important one. Sigma I dual is equal to sigma of I. Dual also commutes with gradient. This one is important for the proof, although it doesn't show up anywhere. Let alpha be an isomorphism of local fields. And then we have A and F, A and F1. Alpha identifies the coefficients, the GLN F and GLN F1, and therefore it has these. On the other hand, we have sigma G and F, and because the Galois is identified, we have this, sigma here, sigma F, and sigma F1. This is applied in particular when alpha is an automorphism of F. The important case is when F equals F1. Especially if F1 is what's applied. Okay, now let F prime over F be cyclic of prime degree D. Prime degree is superfluous, but it's enough. So then there are natural maps on representations called base change. This is base change and automorphic production. Let's say A and F prime to A and D F. So these maps were defined in the book of Arthur Clausel, and here this one was given. So the base change in the book of Arthur Clausel was defined by a relation between the character, base change pi and character pi, to which there may be some allusion in the future, and then in Arthur Clausel there's something similar that was worked out, established by Neil and Herb. Okay. Then relation is, so this is for any, there are lots of cyclic extensions of prime degree. In fact, any extension can be decomposed, any Galois extension can be decomposed as a sequence of cyclic extensions of prime degree. And then we have, so let's suppose we have pi and A and F, pi prime and A and F prime. Then we have sigma of BC of pi is equal to sigma of pi restricted to the Vega-Dean group of F prime, and sigma of AI. Pi is the induced representation for the Vega-Dean group of F prime to the Vega-Dean group of F of sigma. And this is not necessary for characterizing the bijection, but it's crucial to proof. Now here comes position L S pi tensor prime this sequence L S sigma pi and sigma pi prime. So each of these has a different definition. Now we're talking about things that have different definitions. Here there's something defined in an easy way in group theory, and compared to something defined in a difficult way, characters. Pi. I don't know pi, it's theta. And that's pi prime. So here, now pi is in a n f and pi prime. It's no longer what it was before. It's in a m f. So m and n are two different integers, but we can assume that n is less than n for not losing any generality. So this is defined. Just this is the Artin-O factor defined for a representation of the Vega-D group. And this is defined, this is a Rankin-Silver tensor-particle function, which is defined by either of the methods mentioned in Galois talk. You can get the same answer, which is nice. Finally, so you remember that I partitioned the representations in any Artin theorem according to the Artin conductor. No, there's no sign of the Artin conductor up to now, but here it comes. The epsilon factor for a representation of the Vega-D group contains the Artin conductor, and likewise on the conductor of a representation, whatever that is, defined in a rather difficult, complicated way, containing the epsilon factor. So let C be an additive character, and then epsilon of S by tensor pi prime, the same as here, C is equal to epsilon S sigma pi tensor sigma pi prime C. And in particular, taking m equals 1 pi prime trivial, this implies that A pi.
What does normalized mean?
Where is it normalized?
There is a Muslim normalized.
Oh, did I say normalized? Oh, normalized means that I think that it's compatible with the normalization of class field theory. That is, yes, that's what I mean by that.
So it doesn't mean
So that it doesn't. So yeah, I mean, so that's these notes are cut from another talk in which I made more of made more fuss about it. Yes, I mean, otherwise we could change the. We're allowed to invert class field theory, and then we get another message. All right. So that's the theorem. Now, what does it not say? What does this not say? So, in contrast with the topic of Diana Schellstadt's talk, the L packets have single elements, and what we're talking about this is a language parameter, and this is a representation, and there's nothing more complicated. Except once you have a bijection, then you don't have to decompose it any further. On the other hand, there's no known expression of a theta p-adic character in terms of sigma, except in some very special cases. So this is one big open question. These are open questions. And then the other one is that there's another way to construct the objects here, or more precisely the objects here, that is by types. And so fact, all of A and F by types as superior above. Conditional implicit. And a version of this given by NER says that there's a representation for each of these supercustal representations. There's a representation of GLN of maximum of the integers that characterizes it, that occurs and doesn't occur in any other. There's no way to read the type from define.
So, no known way.
No, known way. Known way.
One doesn't expect. One expects there to be such a way.
It would be nice. It would be nice. Maybe. Unexpected anyway? But I'm ignorant. I see. You expect it because you're just naturally optimistic. Me too.
Why can sleep on that? Is the first question a precise question?
The first question is precise.
No, I mean, but do you have like an a priori description of theta pi's without worrying what sigma pi's they're attaching? I mean, you just don't have a formula for them at all.
All right, so let's put it this way: there's a formula for the character in terms of the type. That's one way of getting it. So these questions are related.
But it's it's not a very explicit formula, is it? I mean, it's not a formula that writes it down in terms of elements in the conjugacy type.
It's not a closed formula. No,
Not a closed, sort of like an integral formula.
Right.
So it's not a very...
So this is certainly in contrast to the situation for discrete series for real groups, where the analysis of LPAC was based on Harsh-Chandra character form. Here, well, as I said, there are some cases where this is known, but very few. So it's maybe over. In other words, this theory. This theory is really only in its infancy, and I'll explain later. I think it's relevant to the classification of representations of other classical groups. Let me.
So when do you know the second question? When do you know?
I know
Sometimes.
I'll talk about that. I'll talk about that. So consequence. That's the theorem. Anyhow. So remember that I said that the image of an irreducible representation is always a finite. Well, sign of the irreducible representation of the inertia group is a finite solvable. An irreducible image of the inertia group under an irreducible representation is finite solvable. I mean, the group is solvable, but it's not. But for me, it's an infinite order. So that I the supercustal representation of the F. Then there is a sequence F0, 1, Fn with each Fi over Fi minus 1 cyclic prime order, such that I say BC n over BC n minus 1 over BC 1 of I. So we have a base change here, BC 1 over BC n. Let's stick with base change. Is an unmodified principal series. So I say this is a consequence, but historically, this is actually a consequence any of numerical correspondence. And the proof, either my proof with Taylor or any other proof, uses this fact in an essential way to reduce, essentially to reduce the general correspondence to a series of steps using base change a certain number of times and this one once.
When you say that the NES there, 6 was not a character.
No, it's not, no, it's used in the proof. It's used in an essential way in the proof. But no, so NEL proved by an understanding of Whittaker models on the basis of very similar sorts of considerations to the proof of the converse theorem, that these properties characterize the correspondence if there is one. It says there's a unique bijection. One could see what happens. What this rules out is the possibility of representations, several representations here, happening to the same one here. There may be more of these than there are. But the characterization is of a bijection. So this consequence was is part of the proof. But I also point out for those of you who are interested in proving that lists of residually modular Galois representations are modular, that this, by base change arguments, this reduces to a case where the ramification is only of basically no type. There's no need to worry about ramification.
How canonical is this?
Oh, it's not canonical.
What?
It's not canonical.
So you get a variety of principal series.
For different FNs, yeah. Well, I mean, you look at the image of the inertia group, and that's a finite group that defines an extension. I guess if you take that to the FN, then it becomes canonical. If you write the base change in several different ways, if you break this up in several different ways, you get to the same thing. It's because the I divided for B. So, let me illustrate. This is more of a sort of anecdote. Let me illustrate what happens. Types.
Do you really need to use that number if you're proving holistic theory? After all, we start with the Galois representation. So make the of that form, and then you find the correct automorphic form. That's true.
That's
fine.
No, what you do is what you do is you base change. You get to a place where you have an automorphic lift, and the automorphic representation doesn't have bad ramification, and then you won't have to worry about the problems that were solved. There's the original version. Well, in fact, even the version I did with Lazelle and Taylor has a whole lot of special local problems, local conditions that really are unnecessary. Just there because they were there. So this is an A case. An example. So that is to say, is n times p. Then here's a lemma. Sync. No, I better before I give you this lemma, let's get this. Okay. So if, in this case, any sigma in GNF is monomic, that is to say, induced from a character, chi, say, of some extension f prime over f of degree n. So
G0.
What?
In G0.
In G0, right. Any irreducible sigma of this kind is monomic exercise. The lemma of fucking 6 says that, well, because it's a degree n, f prime, it need not be Galois, but at least it's tame. Lemma. So, suppose f prime over f is tamely totally ramified. Chi a character of W f prime such that an induced representation f is irreducible. Let chi 1 chi restricted to f, then W f prime and stabilizer into f of chi 1. And then there's a generalization for partially ramified. And using this, one can classify the pairs chi f prime, which give you irreducible representations. And it turns out that there is a natural bijection, an identification, using this, and the results of Galois on types for the tame case. We find that there's a bijection between the types here are defined by pairs f prime. Right. And these are also defined by, so here we have, this is A0 and F. This is parameterized by pairs f prime and chi, certain f prime and chi, and the same f prime and chi as characterized G0 NF. So Moy thought it would be natural to assume that this bijection is given by this equality. That's Moy's guess, and this is wrong. See how there was to that. Then Riemann showed that this was wrong, and he proposed a correction that stood for about 10 years until Bushnell and Linear found that was wrong too. And so Bushnell and Linear have proved, obviously the f primes are the same as the chi's, have proved the corrected version of this guess in most cases, but I believe that there's still some open, there's still some cases, residual characteristic 2, which are open. So you said that there's that you can identify. And here we've got Galois data, and here we've got a type data. We can identify them, but even in this in the simplest case where there's just something abelian, it's not completely established.
So this is an attempt to try to answer the second question.
That's right.
That's what's known about that.
That's if P is prime to N. So if
So this was a conjecture of somebody's?
this is a conjecture of Moy. I didn't want to, I wrote it. I didn't want to write it.
Question, yeah, okay. Yes.
So he actually conjectured.
Yes.
He actually conjectured.
When is it wrong? Is it already wrong? Like,
I mean, in the cases where it hasn't been established, it's established up to a quadratic character. So it's only possible sign.
so for GL2,
For GL2, it's okay. For GL2, the corrected version is okay.
the corrected version.
I think the Moy's guess may even have been wrong for GL2, but I don't want to. For GL2, in residual characteristic other than 2, you can construct the bijection by a theta correspondence. So that's one construction of the bijection. One construction of not the bijection of A0 NF. So this is A0 NF by types, or by arithmetic geometry. This is the cohomology of those symmetric which is what we do in that's local construction. Local construction. That's what we do in my book with Taylor. Needless to say, there's no way to relate this construction, the cohomological construction, to the type construction. That's another version of the same old question.
That's known for n equals 2.
That's known for n equals 2. Okay, yes, that's known for n.
And p different from 2 maybe.
Yeah, okay. So for n equals 2 and p different from 2, this is known, well, you mean?
Weber. Stefan Weber.
Oh.
But it doesn't apply to the case.
Doesn't apply? Okay, we'll talk about this. So there may be time on Sunday to go into some of the elements of this last of what I mentioned up there. So I want to talk about compatibility with Functoriality. So first, let me just say very quickly the Jacques Langlands correspondence. And I'll just say for n equals 2 because there's that, and we talked about this in this tomorrow. So let's say G equals GL2F, and now G prime is the multiplicative group of a quaternion division algebra. Over F, which is unique up to isomorphism. And then this actually has nothing to do with what I'm saying, but it is relevant to so if I prime is representation here, so here G prime means irreducible representations of G prime, and G prime is compact mod center, so this implies finite equals G prime center is compact. then, by an application of the trace formula, phi prime gives rise to an irreducible representation. Here, this is in A to F, and it's in fact, it's in A0 to F if the dimension phi prime is greater than 1. And furthermore, every I in A0 to F is of this form. So, one fact that I believe we'll see tomorrow is that this map is characterized by a character identity where G and G prime are associated in the sense that, well, essentially they have the same eigenvalues. These are associated regular semi-simple elements. So G is then just a ladder elliptic. And that means that the characteristic polynomial is irreducible, quadratic, and is equal to Cg prime of t defined by verify passing to the algebraic closure. That's irreducible, that's the elliptic condition. And is equal to 0 if G is semi-simple, regular semi-simple, non-elliptic. Which is to say that the characteristic polynomial is reducible. So, this can be related, as I mentioned, to, except for residual characteristic 2, to something Galois theoretic data. This character, in this case. There are formulas for this in Jacques Langlands that were taken from the literature before. So there are analogous relations for n greater than 2 and G prime inner form of GLM. And I think that this has only been completed in the last couple of years. This was proved in the division algebras by Galois and in the 1980s, and I believe, I'm not completely sure, but I believe that this was just completed in the last few years. I don't want to say anything more about that. I have a few minutes to say something about functoriality in other cases. So we have H. Look at H. A map of L groups. And this means that the admissible automorphism means that it maps to the Weber commute. And now if we have a parameter phi in the Weber unit of F LG, then H will be phi is an L parameter. For G prime, and so if you have an L packet, G is supposed to give rise to an L packet for G prime. And so this, for when one of these is GLN, then there's one has information about the L packets, and the question is what can one say about the image. Now, there's some cases where both of them are GLN. So we're supposed to get, so if let's say G equals GLN and G prime equals, so this is GLV, say, this is GL of symmetric square of V, or GL exterior square of V, then there is 0. So we have pi in A and F, then L of S pi S2 is equal to L of S. Let's call this map H star. Map here we have H is called S star and H is called star S star pi. Same for in other words, these we have parameters on both sides, parameterization on both sides, and they're compatible. This is the L function. Now I have to say something. This is not an empty. This is not a tautological thing, because this is defined by independently, either by Langlands or by integral representations. And same for epsilon factors up to a rooted unity. So at least the conductors are right. Let's see, there are similar theorems for symmetric cube and a symmetric fourth power in G. And for GL2 cross GL2 to GL4, this is tensor product is the and there's another one for GL2 cross GL3 to GL6, and that's due to K. Again, this sort of statement only has content if one has an independent, purely automorphic definition of the object on this side. Now, I don't have time to say what I want to say, which is what happens if G prime equals GLN and G is something else. For example, G is equal to a, let's suppose, so this was, for example, if N is even, then G could be SO2, so N plus 1, or SON. Here the L group is G is equal to SPN, and the L group here is SN. two homomorphisms there. And if n is odd, then you've got G equal to SP n minus 1, and then LG S O n. So the idea is that starting with the parameterization here, consider or construct a map from, we'll call it A of G, A of G prime, and consider the fiber over, you think of an element here as being parameterized by here to the fiber. Star. And this would be a way to construct it.
Questions? It's sort of related to this, but it's, in some sense, it's a question of ignorance that I should know. If I open up Morel's article in Corvallis, it says the local Langlands conjecture is the following. There's a bijection that satisfies 5 representation of theoretic properties.
I
Is it clear
believe,
that this is the same?
well, it does satisfy these properties, and it satisfies additional properties.
Okay, but it does satisfy all of those.
Including the result on tempered and
Oh yeah, that's good. Because that's, it's known for the discrete series of GLNs is already constructed by Galois.
So all those conditions are satisfied. I mean, I've never checked.
But that was not sufficient to characterize the
No, I know that. No, I just, I've never checked if these were actually the same.
Now, I don't know that's I assume Galois has constructed at least tempered alpacas for unitary pairs, and I assume that she checked those conditions.
But the last condition is some compatibility with matched with finite kernel and co-kernel. Could that have been checked?
That's another issue for GLN.
So, for GLN, there's no.
When would that arrive?
I don't know.
I guess GLN was pretty. If not from GLN or something else.
This is functoriality for general Langlands, local Langlands
Just-
for
just-
general groups, or is it just for GLN?
Well, so, I mean, the statement is
For general.
local language in general.
So that condition probably is not relevant. Probably.
So it's not even relevant for GLN.
Yes. There's no match.
There's nothing that will fit.
Right.
Took it.
Well, I hope it's not